Hello everyone, this is Senior 4 Chemistry class and we are continuing with Unit 4, Covalent Bonding, and today's lesson is simple molecular structures and giant molecular structures. Simple and giant covalent structures, you can call them covalent structures or molecular structures, it's all the same. Now, as usual, let us have a look at the objectives of our lesson. At the end of this lesson, you should be able to explain what simple and giant covalent structures are and describe how the type of structure affects the physical properties of compounds. Normally, covalently bonded substances fall into two main types. The first one is simple molecular or covalent structure, and the second is giant covalent or molecular structures. Now let's have a look at the details of each structure. Simple covalent structure. A simple covalent structure is when a substance is composed by a small number of atoms which are bonded to make discrete molecules. And in these molecules, only a few atoms are held together by strong covalent bonds. When you analyze those molecules, you find that the number of atoms, which is shown in the molecular formula, is exactly the number of atoms you find in the molecule. So if we say that we have carbon dioxide, which is composed by one carbon atom and two oxygen atoms, that is a single molecule, which is exactly composed by three atoms. Here you can see a molecule of carbon dioxide. We have carbon and oxygen, and carbon is covalently bonded to the two oxygen atoms. So it is a simple structure. And as I said earlier, the number of atoms in the molecule is equal to the number of atoms in the molecular formula. This is to mean that in some molecular formula, the number of atoms which is written is not equal to the number of atoms we find in the structure. But for simple covalent structures, the exact number of atoms you find in the molecule, in the molecular formula, is exactly the same as the number of atoms you will find in the structure. And that is the reason why they are called simple structures. Now, what are the physical properties of these simple molecular structures? Simple molecular structures, they have low melting and boiling points. Why do they have low melting and boiling points? This is because they have weak forces which join the discrete molecules together. In the substance, we have so many molecules. In chemistry, we don't deal with a single molecule. So when you have a sample of a substance, you should know that there are so many molecules in that sample. And the molecules, when we have simple structures, they are joined by weak forces. And if you have to melt or boil that substance, you have to weaken those molecules, those bonds, those weak forces which hold the molecules together. So if the forces are weak, then it is very easy to melt the substance or to boil it. And that is the reason why they have low melting and boiling point. So it requires a small amount of energy to separate the molecules and hence melting or boiling them. The other property is that they have poor electrical conductivity. Why do they have poor electrical conductivity? This is because they have no delocalized electrons. And even when they are dissolved in water, they do not separate. Some of them do not separate into ions. Why? Because they don't contain ions. So they cannot conduct electricity because they don't have either delocalized electrons or free moving ions, which can be produced when they are dissolved in water. But then here we have some exceptions for substances which are highly polar. The simple molecules which are highly polar can dissociate in water, and in that case they will conduct electricity because they contain free moving ions. We can take the example of all acids like hydrochloric acid, sulfuric acid. When they are dissolved in water, because of being highly polar, they release ions which will help in the conductivity of electricity. What about their solubility? Like all covalent substances, most of them, they are insoluble in water and all other polar solvents, but some of them are soluble. And if they are soluble, it is only because they have some attraction forces which are generated when they are mixing with or when they are mixed with the solvent molecules. So if they can generate some similar interactions between the molecules themselves and the molecules of the solvent, then they can be dissolved. But this is for some molecules only, some simple molecules only. We will discuss this later when we will be studying the intermolecular forces in details. But then here we have to retain that generally simple molecules are insoluble in water, but soluble in organic solvents. As I was saying, simple molecules which are insoluble in water, you find them to be soluble in non-polar solvent, such as hexane, benzene, or alcohol, different alcohols like propanol, ethanol. Those simple molecules which are insoluble in water, they are all soluble in non-polar solvents. What about the second type of structures, the giant covalent structures? Giant covalent structures are formed when we have so many atoms in the molecule which are joined by strong covalent bonds to form a network of bonds in a three-dimensional giant network or giant structure. And then we call them giant covalent structures. In these structures, there are so many atoms connected by many covalent bonds in a single molecule, as we will see on the picture below. And the number of atoms per molecule, it depends on the size of that molecule. Differently from what we have seen before, for simple molecules, we said that a simple molecule has exactly the same number of atoms as the one we find in the molecular formula. But for these giant structures, the number of atoms per molecule will always depend on the size of that molecule. If the size is big, then you get so many atoms per molecule. And if the size is small, you get a small number of atoms per molecule. The most common giant molecular structures are the two allotropes of carbon. Here we have diamond and graphite. And another example is silicon dioxide, the common sand, the sand we know. Here, down here, we have an example of silicon dioxide, the diagram showing silicon dioxide. And this silicon dioxide, you can see here we have 3 atoms. The blue balls are representing silicon atoms, and this one, the brown one, is representing an oxygen atom. And you can see that we have so many atoms bonded together in the structure. It is a three-dimensional structure, and with so many covalent bonds and so many atoms. As you can see, here we don't have atoms bonded, here we don't have atoms bonded, and this is because of the small portion of the diagram we have taken. If you take a big diagram, which will be representing a big sized molecule, then you will have more atoms. But here we have a small number of atoms because even the molecule we have considered is too small. And you can see here, the molecular formula of this silicon dioxide is SiO2. But in the structure, you can see that we have so many silicon atoms. 1, 2, 3, 4, 5, and so on. We have so many oxygen atoms. 1, 2, 3, 4, 5, 6, and so on. While in the molecular formula, we have 1 silicon atom and 2 oxygen atoms. And this is to mean that in the giant structures, the molecular formula which we use is simply the empirical formula. It represents the simplest ratio to which the atoms are combined. It doesn't represent the actual number of atoms in the molecule. So that is the reason why we call them giant structures. Here we have to note that something which is very important, that all ionic compounds and all metals, they have giant structures. You can never find an ionic compound in a simple structure or metals in simple structures. And this is because in ionic compounds, we have so many ions joined together to form a giant three-dimensional structure. And even in metals, we have so many cations and the delocalized electrons combined together to form the three-dimensional structure. Diamond. What are the characteristics of diamond? What are the physical properties of diamond as one of the examples of giant covalent structures? Diamond is a form or an allotropic form of carbon in which each carbon is tetrahedrally bonded to 4 other carbon atoms. Let us consider this atom here. You can see that it is bonded to 1, 2, 3, and 4 other carbon atoms, and the structure is tetrahedral. So in a three-dimensional structure of diamond, we have each carbon atom, which is bonded to 4 other carbon atoms. Here we have the structure of diamond, and this is explaining the graph we have here. Each black ball represents a carbon atom, which is bonded tetrahedrally to 4 other carbon atoms. Now, what are the physical properties of diamond? Diamond has a very high melting point, and this is because to melt the substance, you have to weaken the bonds, or you have to weaken the attraction forces holding the atoms, the particles together in the substance. And because here we have so many and strong carbon-to-carbon covalent bonds, it will require a big deal of energy to weaken those bonds and melt the substance. So that is the reason why this diamond has a very high melting point. It is extremely hard, and if it is extremely hard, it is for the same reason as having very high melting point. It's because we have a very big structure with so many covalent bonds, and then making the three-dimensional structure very strong. We have so many bonds and so strong bonds. It is a very poor conductor of electricity. Actually, it is a non-conductor. And this is because it has no delocalized electrons. As we have seen on the diagram representing diamond, we have seen that each carbon atom is bonded to 4 other carbon atoms. So all the valence electrons are used in making bonds. So we have no delocalized electrons to participate in electrical conductivity. It is insoluble in water and in organic solvents. And this is because it cannot have any interactions with the solvent molecules. The solvent molecules, when they are interacting with that diamond, they cannot make bonds which are, or attractions which are strong enough to weaken the bonds in the diamond and dissolve it. So it is not possible to dissolve the substance either in water or organic solvents. What about graphite? Graphite is another allotrope of carbon, and contrary to this diamond we have just analyzed, graphite has it has each carbon atom which is bonded to 3 other carbon atoms. And as you can see on the structure, we have one layer here. This is the upper layer and this is the down layer. And here we have, this is the bond joining the 2 atoms. This is another bond joining the 2 atoms. And if we consider this atom, you can see that we have one bond here, another bond here, and another bond here. So each atom is bonded to 3 other atoms. And this means that we have hexagonal rings in the layer. Apart from the bonds we have here, we have other attraction forces, but which are weak, that join the 2 layers. And we shall discuss these ones in details when we'll be studying intermolecular forces. But for your information, they are called the van der Waals forces. They are very weak intermolecular forces. Here there is something very special. Each carbon atom has made 3 bonds. What about the 4th valence electrons? The 4th valence electron is delocalized. So it doesn't belong to any of those atoms. It is free to move. So it is free to move in the layers. And as we said, the layers are held together by weak intermolecular forces that we will discuss later in this unit. Now, what are the physical properties of this graphite? It has a very high melting point, and this is because of the giant structure. Every time when we have a giant structure, we have so many atoms joined by so many covalent bonds, and the covalent bonds which are also strong, and then it requires a big deal of energy to weaken those bonds and melt the substance. It is soft, slippery, and it is used in pencils for that reason. Because of being slippery, it is used in pencils and as a dry lubricant for things like locks. And this is because the layers we have seen, they can easily slide over each other due to the weak forces that hold them together. Those weak attraction forces which hold layers together, they are very weak that the layers can easily slide over each other and then make the substance become soft or have a slippery feel. It has a lower density than diamond. And why is it like this? It's because of those layers and the weak forces which are holding them together. We have some empty spaces between the layers, and then those empty spaces, they will make the volume bigger while the mass doesn't increase much. And then you will find that as the mass is not increasing much, while the volume is becoming bigger, then density decreases. That is the reason why it has a lower density than diamond, because a large amount of space is wasted between the sheets or between the layers. It is insoluble in water and organic solvents. And this is the same, just like for diamond. It is because the attractions between solvent molecules and the carbon atoms can never be strong enough to overcome the strong covalent bonds in graphite. So if the attractions between water molecules or the solvent molecules and the solute molecules are not strong enough to weaken the bonds in the solute, then the solute cannot dissolve. And that is the reason why this graphite, being a giant structure, it has so strong bonds and it cannot be dissolved in water or in organic solvents. Conductivity of electricity. Graphite is a very good conductor of electricity, and you know the reason. I'm very sure you know the reason. It is because of that delocalized electrons. We said that the fourth electron is delocalized. So that electron is the one which is responsible for conducting electricity in the solid state. Here we have to note that graphite is is the most common covalent substance which can conduct electricity in the solid state because of having those delocalized electrons. Now, this is the end of our lesson, and I want to give you some time to try these exercises. If you have some questions, I'm very sure as we used to do it, even in class, you have noted them down, and now you are going to try the exercise. And after like 1 hour, we will come back to have a video call via Zoom, and then we will answer all the questions you have encountered, and we will also correct the exercise. Thank you very much. Have a nice work.